So good afternoon, everybody, and I thank the organizers for having me here. So far, we have heard of various ways of how to create metric perturbations, either in the form of tensors or in the form of curvature perturbation. Here, I'll talk about how you can make particles out of these perturbations. So that's the story. And I would like to apply this specifically to dark matter, because in the end, dark matter is dark and we only know its existence through gravitational interactions. And I would like to apply that idea to dark matter. So we all know dark matter exists, and there is evidence for dark matter at various scales. At gigaparsec scales, we know it from CMB. At cluster scales, we know it from lensing and so on. And at galaxy scales, we know it from rotation curves. So all of these are basically gravitational interactions. You can ask the question, when you open the PDG, of course, you don't find anything of this sort because we don't know anything. The only thing we know is that it has no electric charge or extremely tiny electric charge, very, very small. No color charge, must be non-relativistic at the time of first structures, and lifetime longer than the age of the universe. This is roughly what we know. And if we think it's a particle, it already tells you it's evidence for physics beyond the standard model in the form of elementary particles. Okay. So what is the problem? The problem for dark matter is we don't know the scale, and it's a problem of plentitude. For any scale you pick, there are like 1,000 predictions, and most of them rely on non-gravitational interactions. So an exception could be Wimzilla, where it's produced only through cosmological gravitational production. Most other things, they rely on some non-gravitational interaction. Okay, so what? So we can ask the question, how dark can dark matter be? So really dark matter is really only gravitational interactions. We cannot be darker than that. So, okay. So given this assumption, I would like to go over how to make these particles. So there are a few existing mechanisms, some more famous than others. The first example is, I'll go into these things briefly in the coming few slides. So the first example is gravitational freeze-in, where you exchange a spin to particle in the early universe and you freeze in dark matter from the standard model bath. The second one is gravitational particle production. You need massive particles, and basically you're making particles, pulling it out from the expansion of the universe. And it's quite old, and there are many refinements and many new things. I would urge you to look up review by Andrew and Cole. The specific thing I would like to talk about now is from perturbation. It's a recent paper we put out earlier last year. It's basically termed stochastic production from curvature perturbations. I'll go into details about how this works specifically. So there was also a competing paper which came out a few months before us, but they look at tensor perturbations. I think both of them put together, they form a nice story. And the formalism, what we do is we use Bogolubov transformations to compute things, while in this paper with Azadeh and Joachim, they do more in formalism for tensor perturbations. Okay, so what is this gravitational freeze-in all about? So we have a standard model bath in the early universe, and you have 1 over m Planck suppressed couplings, so directly H mu couples to the stress energy tensor, and you can write down the amplitude for such a diagram. And you go through the motions, you compute the cross-section, and you can directly compute the yield. Because this is a freeze-in mechanism, the right-hand side of the Boltzmann equation is simple, and you can directly integrate the Boltzmann equation. What you'll find is that the yield, because I'm specifically focusing on conformally coupled particles, the yield is simply proportional to the conformal charge and the reheating temperature to a strong power, that is 3. So conformal charge for a real scalar is like 4/3, for a Weil fermion is like 4, and for vectors it's 16. So from the yield you can compute the abundance, and you'll see that dark matter abundance goes like this. So if you demand this to be equal to 0.25 or whatever, you'll get a relation between reheating temperature and the mass. So larger the reheating temperature, smaller the mass, and well, also the larger, it's a spectrum, it's a lower bound. So this mechanism basically depends a lot on what you assume for the reheating temperature itself. So you go through you work it out, the previous equation, and you end up with something like this. So for 10 to the 15 GeV reheating temperatures, you find that Rayleigh abundance is produced for 10 to the 6 GeV dark matter masses. So a typical candidate is basically glue ball dark matter. Well, QCD glue balls, we have not seen it in the experiments, but it can be dark matter, now, hypothetical SU3 dark, and you can look up this paper for more details. These are color singlets made of gluons from self-interactions. In this sense, it's really dark. This is like SU3 dark, or any confining SUN will give you something like this. Okay. So let me move on to the second topic, gravitational particle production. That is more relevant. The basic ideas there are more relevant to what follows. The basic idea for the gravitational particle production goes, you can understand it through Schwinger pair production. So basically, if you have a strong background field, if the work done by the field over the Compton wavelength of the particle is of the order of the mass of the particle, you can in principle create particle pairs, basically pulling it out of vacuum. This is an explanation for how pulsars produce electron-positron pairs, for example. But you see, like, making such an experiment at Earth is close to impossible because you need some insane voltages, like 10 to the 18 volt per meter. Okay. So gravitational particle production is similar. So instead of a strong external field, here the external field is expansion of the universe itself. So you can have particle pairs that is produced, and as the universe expands, in principle, you can pull it out. So this depends on the mass of the particle and the rate, the Hubble rate of expansion. So how does this work? So it's easy to say, but you can do this quantum mechanically. So in the next few slides, I'll spend some time going through the mechanics of this, as in just building intuition first. So the point is, it's basically, you can imagine a harmonic oscillator, but with a time-dependent frequency. So what does it mean? It's that because the universe is expanding, the initial vacuum is not the same as the final vacuum. So to compute the particle numbers and so on, you have to relate the two vacuum and evaluate the particle numbers. So how do we do that? So this is the Hamiltonian. Pick up any quantum mechanics textbook, you'll find this. So, and conjugate momenta. And the key thing is we have a mode decomposition in terms of creation and annihilation operators. There's a star somewhere I'm missing. And you plug into the equation of motion and you get the mode equation. So the key thing of cosmology is that we assume an initial vacuum, so-called Bunch-Davies vacuum, where you have only positive frequency solutions, basically decaying modes, and A annihilates the initial vacuum. So at late times, there is mode mixing, and another part develops at far infinity. So this is the basic idea. You can look up famous papers by Parker and Ford, very long ago. And these coefficients, alpha and beta, are often referred to as Bogolubov coefficients. And these are the key parameters that relate your initial vacuum to the final ones. Are there any questions at this moment? Anyway. Okay. So then so as you notice here, this was the initial wave. And through mode mixing, you have developed another part, the negative frequency part. And occupation number is given by beta square. And notice that the vacuum here, it has to be evaluated in the same vacuum. So it's on the initial vacuum. So number density and energy density are directly related to beta square. So you see the differential number density is k cube beta square, and differential energy densities k to the 4 beta square. So this is basically the quantum mechanic intuition. So in QFT, it is similar, but you need to go into a little more technicalities. And for QFT in curved spacetime, you can see it as particle production. So this is my basic setup. I have a massive fermion conformally coupled to the metric. This is the usual FRW metric. Notice that FRW metric has a while invariant because you can absorb A square through a simple transformation. And what we consider here is a while fermion. So this is written in two-component notation, and the coupling to curvature is through the spin connection omega. So naively, if you rescale the fields through the while weight, you can, through a while transformation, you see that the Lagrangian or the action doesn't see the time dependence of the metric. So that's the, so we work in the redefined field, and this is what we get. This is the equation of motion. As done before, we apply mode decomposition to these fields and derive the mode equation. So here we see that the characteristic frequency is k square plus m square a square. So this is how you get time dependence on the frequency. So at this level, it's really the same as the quantum mechanical harmonic oscillator. So from here, once we know this, we compute the Bogolubov coefficients and obtain number densities and energy densities. Okay. So the key point is that the production here is peaked at when the Hubble rate is roughly proportional to the mass. So the wave modes, when the wave number is roughly proportional to A times mass. So radical abundance in this case is a similar formula as for the gravitational freezing, but the prefactor here is different, and it depends on this quantity. This Km is nothing but Am times scale factor times M. It depends on that instead of reheating temperature. In principle, they can also be related to the reheating temperature through a direct relation. So this mechanism depends on the mass. And as you see, the production is peaked. Production typically occurs when mass is 10 to the minus 2, 10 to the minus 1 Hubble rate. So here it's written in terms of dimensionless. This is the wave mode. My question is, what determines Kmax? Kmax is just a number. It's a mode. So this is when the production is peaked. So this is the K.
But the Hubble parameter is a function of time. So
no, this is a function of time, yeah. So there's a scale factor dependence. You have to work it all out. It happens deep in radiation domination after reheating or at that point. So
I don't understand. So Hubble parameter is peaked at the,
not the Hubble parameter. Not the Hubble parameter is not peaked then. The particle production rate is peaked. So this d rho d log k, which is this function here. So there is the Bogolubov coefficient here that depends on k. This function is peaked. So Hubble is whatever it is. So this is the parametric understanding of when I maximize this quantity as a function. No, I mean, Hubble today we know, we assume simply radiation domination. And you know, whatever the scale factor, you know the Hubble parameter then. So the peak is determined by the Bogolubov coefficient, as in how it looks. You have to go inside of, I haven't written the functional form. Okay. Maybe in the next few slides it becomes clearer. Okay. Where was I? So what I wanted to ask is, so this mechanism depends on the mass. And if I make mass 0, the production in this mechanism is 0. As in that you see it here, if I make mass 0, I don't have a time-dependent frequency, so it's like a free wave propagating in vacuum. So we found that there is a mechanism where you can produce particles even when they're massless. So this is what we call stochastic particle production. And the key understanding behind this is that the mass term breaks Weyl invariance and makes produces particles through gravitational particle production. So there are other sources of Weyl invariance breaking. So one obvious thing is if gravity is dynamical, that is when you have such a term in the Lagrangian, Ricci times m Planck square. The other possibility is fluctuations on top of the FLRW matrix. So these can come in two flavors. One is curvature perturbations from inflation and tensor perturbations from wherever, specifically phase transition. And let's see how this works. So now the new metric is the same as before, but now I have two functions, phi and psi. These are the scalar perturbations. And as you clearly see that this cannot be reabsorbed from a trivial transformation. So a field redefinition will take a square dependence out of the action, but you cannot get rid of phi and psi from the action itself. So phi and psi are these generic functions of time and space. We don't make assumptions. In principle, it's a power spectra that matters. So for the discussion that follows, I'll simply assume that there is no anisotropic stress. So phi is psi, that just simplifies some mathematics. Okay. So how do we do this? So that means we have to evaluate the Weyl equation more carefully in curved spacetime, where these E mu's are tetrads and W omega mu is the spin connection. So you plug in through that line element, you can know what the tetrad is and you can derive the spin connection. And when you go through the motion, you get an equation of this sort, where J is now a source term. So this is in coordinate space. What I've written here is in Fourier space. And this psi is the scalar perturbation, and this chi is the fermion, is the mode equation. So we solve this equation iteratively by plugging in the vacuum solution, that is the Bunch-Davies solution on the right-hand side, and evaluating the source and the Bogolubov coefficient that follows. Key thing is that the source term breaks Weyl invariance. As you see, this behaves like a mass term, very similar to the gravitational particle production I showed. But the point is that since this is a stochastic perturbation, on average this is 0, but its square is non-zero. That's what we will exploit. Basically that's what we'll use to show that Bogolubov coefficient, square of Bogolubov coefficient is not 0, and you get particles from this mechanism. So in other words, there is translational symmetry that is broken, and basically that makes particles. Okay. So let me go into a bit of details about how we compute this. This is the vacuum equation, that is e to the minus ik tau, and this is the correction to the original solution, to the vacuum solution. We compute this using the retarded Green's function, and inside the source we plug in again the vacuum solution, the usual iterative procedure. And of course tau here is the conformal time, and we integrate from infinity to minus infinity to tau. So again, the Green's function, this is the standard Green's function for any fermion. Pk minus and Pk plus are helicity operators. So from here, you can evaluate the Bogolubov coefficient by projecting on this part of the Green's function. You can directly extract this. And here you'll see that the Bogolubov coefficient, here it's the differential Bogolubov coefficient, is proportional to psi, the perturbation itself. And all of these algebra, you can reduce it to something simple like this, where we have used integration by parts to remove the time derivatives on this. Because far in the past, there is no perturbation. Far in the future, there is nothing, something happens in between. That's what we use. That's why you can use integration by parts to remove it. And these psi's are basically eigenstates of the helicity operator itself. So you see here more clearly that the Bogolubov coefficient is proportional to the perturbation. And if the perturbation on average is 0, because it's stochastic, this coefficient is 0. But the square is not. That's the key point. Maybe at this level, it answers your question in some sense.
Well, this is weird, but this doesn't answer.
Okay, then we can, okay. Okay, so where was I? So now we have the differential Bogolubov coefficient. Now I'll show you how the Bogolubov coefficient square looks. So the square is basically the square of it, and the average is over the time. And inside of it, you will find that there'll be psi and psi star, and this is basically the expectation value of it, or the 2-point correlation function. And we relate this to the primordial curvature power spectrum through this. So this comes out of momentum conservation, of energy conservation, and so on and so forth. So you see that this function depends on the primordial curvature perturbation through this function delta psi, and a kinematic kernel called kappa. And this kinematic kernel depends on the type of particle, but it's meaning on the spin, meaning type of particle, but typically it's a function of this sort. And delta psi is basically the power spectrum when production at late time tau, but then this is related to the primordial curvature power spectrum through the transfer function. So you have to plug this all in to finally evaluate everything. You can notice a few more things here. One thing is that the kernel, I've introduced something called omega without specifying it. Omega here is nothing but k minus q. So the way to interpret this is that a mode k is created through mode omega, where momentum or energy is transferred from the perturbation at value of q. That's how you understand this. So omega is k minus q. These are vectors, so that's why you also get an angle here. Roughly, when you look at this, at large momenta, this whole function goes as q to the 4 over k square. This will become important later. Okay, you can do a little bit of massaging of the equations and plug in the beta square in the number densities, in the expression for the number density I showed before. Do the time integrals. The time integral, as you see, the conformal time, it only sits in the transfer function and not in the kinematic kernel. And so you can rewrite it in this way, where this contains the time integral. And you'll have a differential number density of particles given by this formula. Here I show an example of how it looks, where we have assumed something special for the perturbation. So if the primordial perturbation is a delta function, peaked at some scale q star, you'll see that the normalized distribution, number distribution, differential number distribution looks like this. The delta function one is the black curve. It has a peculiar peak, which is peaked at k over q star equal to 1. Remember that k is the momenta of the mode that is produced. So n equal to 3, n equal to 4, these are different functional forms, like phenomenological functional forms for the curvature perturbations we have used. So these functions goes as q over q star cube divided by 1 plus q over q star to the 3 plus n. It's a function of that sort. The key point is that Qmax is not infinity. Qmax is meaning the maximum momenta of the mode of the perturbation is set by what happens during inflation. So it's always, we do not know it exactly, but we know it is regular. And we showed these plots for the other two cases for when and Q max over Q star is 10 and 100, and we see these features. And for these two cases, the production is peaked, or the spectra is peaked when Q over Q max is order 100. Wherever Q over Q max, what we choose here, that's where the function will be peaked. So to get the relic abundance, that's what we'll do next. So coming back here, so you can do all the time integrals. You can also do the angular integral here. After performing these things and using the fact that the kernel goes as Q to the 4 over K square, all of that can be reduced to a simple equation of this form for the number density of particles produced. And very interestingly, all of that mathematical part A turns out to be a number of the order 10 to the minus 2, which is quite neat. And this number does not depend too much on the type of particle. In the end, it just depends on the conformal charge times this number, roughly. Okay, so now we can ask what should be the characteristics of this scale Q star such that the number of particles produced reproduces the dark matter abundance. So that means I multiply this by m divided by critical density, all of that, and I impose it to be 0.25, and I get relic abundance of dark matter through this stochastic production mechanism to be of something of this form. So once you impose that, you can rewrite everything in terms of what is the required Q star, that is the scale at which the curvature perturbation is peaked. We find that this is a very small number in terms of length. This is 10 to the 22 megaparsec inverse. So this roughly is something like 100 meters, as in if you put in all the numbers. So you see, for this mechanism to give you dark matter, the right dark matter abundance, you need a very strong power spectra, highly peaked power spectra at very small scales. And we find that typical masses that we can get out of this mechanism is 10 to the 6 GeV with amplitudes of the power spectra of the order 10 to the minus 2. So that's what I said earlier, that we need a sizable primordial power spectrum to generate these particles. And interestingly, this happens during the last few E foldings of the inflation. As in this, you can see by simply taking the log of Q star over H0, Hubble today, and you find this to be roughly 59 point something. So really, these are the perturbations that exited the horizon in the last E folding of the inflation. And if this is large, then you can make particles out of this. And interestingly, this is also related to slow roll scenarios. For example, even for primordial black holes, you need something similar. Maybe not something at such small scales. You can get away with even larger scales, not like 10 meter scale or 100 meter scale. And yeah, there are many phenomenological ways to get this. We are looking into that, how to make them from phase transitions and so on and so forth, different models of inflation. Other point is that, notice that when these particles are produced, they are massless. So they have to acquire mass at a later stage somehow. That means they have to be embedded in some theory where something gets a wave and becomes massive. So probably there's a phase transition in the dark sector. We don't know much about it. But this is what is required to make stochastic particle production work and give you dark matter particles. So this is like a rough summary. Maybe I'm a bit early, but it's okay. There are three mechanisms, and here I list like expression for relic abundance of dark matter in these three mechanisms. Notice that all these formulas they look similar. In the first case, you depend on reheating temperature through this Kr. In the second formula, you depend on the temperature at which m when K is A times m, and of course there is this additional term which I didn't put in before, that if this is produced during reheating, there's some dilution, so that's the dilution term, but that's not too relevant. But what we care about is simply the parametric dependence. And the stochastic particle production is of this form. So the key feature is that it doesn't depend on details of reheating, but it only depends on the power spectrum you get from inflation itself. So in that way, we have one less parametric dependence on a parameter, and it's quite nice. So this brings me to my conclusion. So massless particles can be gravitationally produced from perturbations, mostly because perturbations break while invariance of FLRW, and possibility that dark matter is coupled only gravitationally is compelling, but it's not good news for people who look for dark matter that rely on non-gravitational interactions. So thank you for your attention.
Next, thanks, Raghuveer. Questions?
So I understand that one of the requirements for your scenario to work, I mean, for dark matter production or for production of anything that's possible needed in the early universe, is that there is an increase in the scalar power spectrum.
Yeah.
And if we have an increase in the curvature power spectrum at the end of inflation, this typically crosstalks to the amplitude of gravitational waves. Is there any constraint coming from such considerations?
Not really. We do not, constraints at small scales are very poor. And whatever, it depends on the tensor to scalar ratio for gravitational waves that is set by the model of inflation. But as I showed you, this is like 100-meter level of perturbation. So really at this level, I don't know if there's a cool way to constrain such perturbations. That will constrain the scenario right away. But yeah, I don't think it's a concern.
This is similar in spirit to the last question. So, I mean, what about the formation of primordial black holes from the large curvature perturbations? Do you expect there to be primordial black holes? Would they make up an appreciable population?
We do
of dark
expect
matter?
primordial black holes. Maybe from here I can say something. So if the amplitude is smaller than 10 to the, let's say at this scale, I use the exact same spectrum, power spectrum, to compute the abundance of primordial black holes and their mass. The thing is, the perturbations are so small that primordial black holes you form are very light. So most of them evaporate by now. That is one. Of course, you can find ways to do things. If the amplitude of the power spectrum is smaller than 10 to the minus 3 minus 4, it's quite very easily this mechanism dominates over primordial black holes. Even if you think of some crooked way where you can still get heavier primordial black holes. If the power spectrum is smaller, this mechanism dominates. Maybe you have to reach scaled m from 10 to the 6 to something else, but this will be dominant. So we don't know the full story yet. We're still working on it, on how to stitch these things. But analytically, at this level, we think that primordial black holes that are formed at these scales should not survive by now. They should.
There's some dark matter production from their evaporation. I guess that's negligible.
Yeah, that is there. That is inevitable.
Is it correct that in this mechanism you have to turn on the fermion mass at some point? Because you initially assume massless fermion and
yes.
The final expression you have. And do you have any comment on the mechanism for mass generation?
The working assumption is that this fermion sits in a secluded dark sector, and somehow that sector gets a web, and that generates the mass.
So it happens after the production.
It comes after production.
You don't specify.
We don't specify.
You don't specify. Okay.
Yeah.
And another question is: do you expect any isocurvature from this isocurvature, or such isocurvature from this kind of production mechanism?
From the production?
Yeah, from this dark matter production mechanism.
There will be some. I don't know. I've not thought about it more carefully about it. Whatever it is, I think it'll be smaller. It won't be too much.
Okay.
But on the other hand, you can use isocurvature perturbations to enhance production.
I see.
So this the dark matter production is, I hope, all standard model particles also produced in the same way, right?
So in this mechanism, all particles are produced.
So because if it is from the curvature, so universe will not choose only dark matter.
Yeah.
So it will produce everything, right?
Yeah, so the mechanism is general. We chose dark matter.
It will not choose only dark matter, right? It will choose everything.
Yeah. But the point is that for other particles, because they're more strongly interacting, this production mechanism is negligible. Because once you have a thermal bath, when inflaton decays, from there, whatever particles you make is way orders of magnitude larger than from this mechanism. Simply because color GS is large, for example.
And so, because this is, you said that was the last of the inflation, right? So they will be diluted to some extent, these particles?
So let's say, so these things, no, the perturbations are produced at the end of inflation, but these perturbations enter the horizon during reheating or after reheating, and that's when the particles are produced. So if the perturbations re-enter during reheating, we find that if you work through the whole story, through the transfer function and all that, we find that in this mechanism, the dependence on the reheating process itself is not relevant. I mean, it's too slow and it should not matter. But if you produce at the very beginning of reheating, of course, there'll be some dilution. That is a given.
Am I audible? Okay. So my question is regarding the gravitational particle production. So you said that expansion drives the production of particles. So how does it depend on different epochs? Can we produce it in the matter-dominated epoch also? And another question is that this gravitational production, where does it stop? Because if it is happened in every epoch, then there is a fear of just overclosing the universe with dark matter. So how this production stops eventually?
So for this mechanism to work, you need time varying background. So as long as there is time variation, this production mechanism is active. This is a very long picture to explain, but maybe this helps. This is a cartoon of log of scale factor and co-moving distances. So inflation happens here, like there. And we are looking at some patch where you are in radiation domination, it's increasing. Kr is the mode that enters during reheating, and Q star is the perturbation. And particle production is active when psi evolves. Psi is being the perturbation.
Okay.
And so it depends on when the perturbations re-enter the horizon with respect to Q star. So typically this mechanism will end depending on what are the masses and so on and so forth.
Okay. Okay, thanks.
But as universe expands, you form fewer and fewer because everything gets diluted in some sense.
If there are no more questions, let's thank Raghuveer and let's break for coffee.